Last time we looked at how you do the pre-processing if you have a Q2 access structure, which is kind of very similar to the honest majority case. Now we've got the issue is the other thing we looked at was in previous times was the full threshold access structures. So we can't use the previous algorithms to do the pre-processing in the full threshold case because the secret sharing scheme isn't multiplicative. So for full threshold access structures, dishonest majority, we've got to do something a little bit more complicated. And that's what we're going to look at today. So how are we going to do full threshold pre-processing? Well, what we're going to do is we're going to go back kind of to the beginning and use Gentry's method for a distributed MPC protocol based on homomorphic encryption. Because pre-processing is itself a multi-party computation problem. It's can you produce random shares of triples? And because that's an MPC problem, we can use an MPC protocol to do that. And what we're going to use one based on homomorphic encryption, which sounds like it might be very inefficient, but because we've got a very simple function we want to compute in pre-processing, that's going to be efficient. So recall, what is the goal of pre-processing? We want to produce multiplication triples, square pairs, these bits and the input tuples. Same as before, nothing different. Now for full threshold pre-processing, as I said, we're going to use a somewhat homomorphic encryption scheme, but we're only going to need a somewhat homomorphic encryption scheme which evaluates circuits of multiplicative depth 1. That means it's not a general FHE scheme, it's just an SHE scheme, and because multiplicative depth 1 is relatively shallow, this is relatively efficient. We then make it even more efficient because we use this method, what's called smart for counter and SIMD packing, to pack as much data into each ciphertext as possible. So each ciphertext maybe holds 32,000 elements, and so we do 32,000 things in parallel. We're also going to use BGV as the underlying somewhat homomorphic encryption scheme because that's just easier to deal with because we're really going to be dealing with large finite fields as the base plaintext space. But if you don't understand any of that, we're going to kind of abstract it away. And we're going to think of the somewhat homomorphic encryption scheme as an encryption function, which is going to take something in a plain text space, which is going to be it's basically going to be this set here. It's going to be a finite field, polynomials over a finite field, modded out by x to the n plus 1, okay? And where n is the power of 2. Then we're going to take a plain text here, which is going to encode n values at once. So think of n as 32,000-ish. We're then going to take some random coins, and we produce two elements in RQ. So we've got RQ and RP. So Q is called the ciphertext modulus, and P is called the plain text modulus. So think of P as like a 128-bit prime. And the Q is a product of primes, which is maybe 700 bits. So each ciphertext is two lots of 700-bit numbers and then 32,000 of those. So that's 2 times 32,000 times 700 odd bits. So this is quite a big ciphertext. Now, those two elements in C0, called C0 and C1, you don't have to worry about encryption, but what an encryption actually looks like is that if you have a secret key, it's C0 minus C1 times the secret key mod Q is equal to M plus P times epsilon, where epsilon is small in whatever small means, okay? So we just have to kind of intuitively think that an encryption produces a C0 and C1, such that C0 minus C1 times the secret key mod Q is equal to the message, which is in this kind of nice ring mod P, plus P times epsilon. So because epsilon is small, there's no wraparound. So then we just take the final result, mod P, so we go mod Q, then mod P, and that will give us our plain text. That's how decryption works. Now the problem is that unlike traditional public key schemes, for example ElGamal, you can think of the C0, C1 as like C0 and C1 in ElGamal, but in ElGamal, every C0 and C1 is a valid ciphertext. It's an encryption of something. Whereas that's not true here, is that the C0 and C1, a random C0 and C1, might not encrypt anything, and that's because there might not exist a message in the plaintext space and a small epsilon such that the decryption equation gives us m plus p times epsilon. So this gives us rise to lots of problems. If we just arbitrarily have a random element in C and we decrypt it, this may reveal information about the secret key. We don't know how, but it may. So because of that, an encryptor needs to prove that the ciphertext they're producing is well formed. In other words, that decryption is going to work properly and it won't reveal information about the secret key. Because if it's an invalid ciphertext, it might reveal information we don't know how, but it might. So that adds a level of complication. So to do that, what the encryptor does is every time he encrypts something, he's going to apply a zero knowledge proof to it. And the zero knowledge proof is going to prove that the message is in some sense well formed. And in Scale and other protocols based like on speeds, etc., we use basically two types of zero knowledge proof. The first type of zero knowledge proof is executed individually by a player. He has an encryption, he has a message and this randomness that he's used to encrypt it. And what he's going to do is the proof is going to output the ciphertext and a proof sigma that the ciphertext is okay enough. It might not be a perfect ciphertext, but it's okay enough for the purposes of the protocol. Okay, and where that means is for the type of homomorphic operations we're actually going to execute, and for the distributed decryption protocol we're actually going to execute. So we're not going to go into what details of what okay enough means is, or what the precise details are, or how you do the proof. But kind of you've got to remember that you're going to add a zero knowledge proof, and this zero knowledge proof is really big. It's really complex. So we really want to run this simple zero knowledge proof a small amount of time as possible. The other thing we're going to do is there's another type of proof we can do, which is a multi-party proof, because what we're going to need is that all players are going to have to encrypt ciphertext. So instead of having to execute the simple zero knowledge proof n times, we can kind of produce a joint proof that the sum of all our ciphertext is okay. So what does this, it's called Top Gear, what does this zero knowledge proof actually do? Well, each player has a message and a randomness, and then they put that into the pot. Each player doesn't know what the other player's message or the other player's randomness is, but they output the sum of those encryptions and a proof that that sum is itself okay. So the proof is done on a sum, so instead of having to do n individual proofs, we do one multi-party proof, and that's so we basically save a factor of n in the execution, and that saves a lot of rounds of communication, saves a lot of data communicated. So Top Gear is what we do when we want to prove something about a sum. Okay. So how is full threshold preprocessing going to work? Now recall, for full threshold, we authenticate shares by doing a full threshold sharing of the value A and a full threshold sharing of the MAC on A, which is alpha times A. So we need an additive sharing of alpha. And we're going to also need an encryption of alpha under our somewhat homomorphic encryption scheme. So the way we do that is we just run the Top Gear protocol, which gives us the encryption of alpha. Each party obtains alpha I, which was their input message, such that alpha is the sum of the alpha i's. And we also get a proof that this encryption of alpha is valid. So this is the first execution of Top Gear, and it gives us not only the individual shares of alpha, but it gives a hidden value of alpha which has been committed in the homomorphic encryption of alpha here. The other thing we need is we need a form of distributed decryption. And the distributed decryption is not really kind of doing distributed decryption. What it actually wants to do is it's really doing a form of resharing. So the underlying key for the homomorphic encryption scheme is not going to be known by anybody, but everybody's going to have a share of the underlying decryption key. So party 1 is going to have SK1, party 2 is going to have SK2. And we're going to have this procedure which allows us to decrypt a ciphertext by a protocol that allows us we have the ciphertext, everybody knows it, everybody puts in their secret key component, and then we output the underlying message. And then we're going to use this to do a form of resharing. And what are those two forms of resharing? The first form of resharing is going to produce an additive share of the underlying message encrypted by the ciphertext. So given C0 and C1, everybody is now going to get a distributed decryption of C0 and C1. And because C0 and C1 are encoding 32,000 things at once, it's actually doing it with one operation. We actually do an additive sharing of 32,000 things at once. The other one, method of reshare, does exactly the same, but it's going to produce a fresh encryption of C0 and C1 at the same time, for technical reasons we'll come to later. Okay, so if we think the secret key is shared like this, then decryption can be done insecurely as follows. Each player just can distribute this kind of partial decryption, which is minus SKI times C1, and then they exchange the MIs, and then they can produce the decryption like this. Now, this will give you the valid decryption, except it leaks a lot of information, because as everybody transmits MI to everybody else, then if player 1 sees M2, then player 1 can work out what SK2 was, because player 1 knows C1. Okay, so they just have to divide M2 by C1 and they'll get minus SK2. So that reveals too much information. So there's a standard trick to use this form of distributed decryption, which is correct but insecure. There's a very simple way of making it secure, and that's using a trick called noise flooding. So how do we do that? So this is how distributed decryption works. This is how noise flooding works. So each party generates a random noise which is really big. You know, it's 2 to sec times the bound on the actual noise. So B is the bound on this epsilon. So if we imagine we go back, where have we gone back to? We go back to here. This B is a bound on the absolute value of all the values in this term epsilon. And then to do the distributed decryption, we kind of multiply that by a bigger number, divide by P, because we're going to multiply by P here. So this P and this P will cancel out. And so this MI dashed is the MI from the previous term plus P times something huge. And this something huge is basically flooding out all of the information on SKI in this. But it's P times it. So when we form this value here, these FIs cancel out, but they only cancel out at the very end. Okay, so that's the kind of trick. It does mean that Q has to be rather big, but this forms a form of noise flooding that basically wipes out all the information in SKI. It's a standard trick used in much of homomorphic encryption. So from that, that kind of trick of distributed decryption, we can now form our first reshare. We don't actually, in the first reshare algorithm, actually have to do any form of distributed decryption, because we just want to produce additive sharings. So given a ciphertext, what does our first reshare method do? Well, it kind of uses the noise flooding trick, but it kind of does it in a clever way. We don't have to multiply by the P here, so because we're basically going to use the FI as the share. So the noise that we're adding in the noise flooding, we're actually going to take that noise and then take it mod P, and that's going to be the shares for everybody apart from player 1. And player 1 is going to kind of adjust his sharing by the values he gets from the other players to give us the correct answer. So the sum of the MIs here will sum up to the MI, the actual M encrypted by the ciphertext. So it's kind of nice and simple, really. Reshare 2 actually does use distributed decryption, because what we do here is we take a sharing of a random value which we take from Top Gear. We then add that onto the ciphertext we're trying to decrypt, which actually gives us an encryption of M plus F. We now decrypt the ciphertext encrypting M plus F to give us M plus F itself. And because F is random, this is basically a one-time pad encryption of M. But from that, we can form a secret sharing of underline M in a kind of a similar way. But also, because we've got M plus F, we can re-encrypt it, subtract it from the ciphertext we got out of Top Gear, and this gives us basically a fresh ciphertext with not that much noise in it, which encrypts M plus F. This gives us this, and then we subtract the ciphertext encryption F, and this will therefore give us an encryption of M. So CT dash gives us an encryption of M. So this gives us the sharing plus an encryption of M. And then from this, it's quite easy to produce multiplication triples because we just need to do multiplication. So how does this work? Well, we get an encryption of A from Top Gear, a random A, which we know is good enough for our encryption algorithm because Top Gear includes the zero knowledge proof. Get an encryption of B. And now we want to produce the sharing of alpha times A, the encryption, the sharing of the MAC. So what we do is we produce an encryption of the MAC by using the homomorphic property, and then we run reshare 1 to get a sharing of that of the thing being encrypted. We could do the same for alpha times B. And now we need to produce the C component. Well, to produce the C component, we multiply A by ciphertext encrypting A by the ciphertext encrypting B. This gives us a ciphertext encrypting C. And now we get the shares of that C by running reshare 2. So what that does, remember, is it gives us the shares of C plus a new encryption of C. Now, why do we need a new encryption of C? This is because we want to produce another multiplication on this encryption of C. And we've already used up one level with this multiplication here. So we need a fresh encryption of C to be able to multiply it by the ciphertext encrypting alpha to get the MAC on C. And so we can execute this protocol, and this will give us the triples ABC. Now here it looks like you're getting one triple ABC, but because the ciphertexts are encrypting 32,000 things at a time, what we actually do is we execute this once and we get 32,000 triples at once. So we might be dealing with very, very large ciphertext, but actually because we've got this amortization that every time we press the button we get 32,000, in practice this is relatively fast. The problem is it's not actively secure. The zero knowledge proofs mean that when we do the distributed decryption, we don't reveal information about the secret key because the ciphertexts are valid enough, but you could still lie. And so this thing here may not be a valid triple. C may not equal A times B, and it may be the case that the MACs are not produced correctly. But we're going to check that later in sacrificing, so we're not going to worry about it for the moment, but this is a passively secure protocol which reveals no information, which is what we really want. So that's how we do with multiplication triples. For square pairs, it's exactly the same as we did before. Instead of taking a random B, you take A, you multiply it by itself, this gives you A squared, same thing. Random bits done exactly the same way as before as we did for the Q2 case. We take a value, we square it, we take the square root, and then we divide, and then we adjust. So it's roughly the same. But as we said, things could still be wrong. There might not be valid bits, the MACs might be wrong, but at least we can produce them in a passively secure manner. Input data is slightly different. What we do here is we run the simple zero knowledge proof to get a ciphertext encrypting A. Everyone produces the encryption of alpha times A, so we get the MAC. And we output the sharing of A to all parties, but party I actually knows A because that's what they did with the simple zero knowledge proof. So this kind of gives us the way to do input data. So that's it. That's how we do pre-processing in the full threshold case. It's a bit like the Q2 case, but instead of using Maurer multiplication, we embed everything in a homomorphic encryption scheme, and then we use the homomorphic property to do the multiplication over there. So that's basically what is usually called the speeds method of full threshold. To reiterate though, both in the Q2 case and in the full threshold case, the sharings that we might get out may be invalid, they might not be truly authentic values, or the triple might be invalid in the sense that C is not equal to AB, or the square pair may be not invalid in the sense that B is not equal to A squared, or it might be the bit's invalid in the sense that the bit is not actually a sharing of 0 or 1. So next time what we're going to do is work out how to fix that problem, how to make sure that this passively secure pre-processing in the Q2 case and the full threshold case is actively secure, and then how to use that actively secure pre-processing to give us the data and how we're going to process that in the online phase. So I hope you kind of followed this, and we'll see you next time.